This video is on complex power series. In today's video, I am going to explain Laurent's theorem. See here, the statement of the Laurent's theorem states that let f of z be analytic on circles C1 and C2 and throughout the region between the two circles. Let Z be any point in the ring-shaped region between the two circles C1 and C2. Then f of Z is equal to sigma n is equal to 0 to infinity an into Z minus a power n plus sigma n is equal to 1 to infinity bn by Z minus a power n, where an is equal to 1 by 2 pi I integral f of z dz by Z minus a power n plus 1 and bn is equal to 1 by 2 pi I integral f of z dz by Z minus a power minus n plus 1. See here, let me show you these two circles. So this is circle C1 and the next one is this is circle C2 and this is the center point and this makes the radius R2. So this is R2 and this one is R1. Clear? So this is the point A. So A is the center point for the circle C1 and C2. So here you have to consider that C1 is greater than C2. Therefore, R2 is the radius for C2 and R1 is the radius of C1. So these two are concentric circles. You know, concentric circles means having same center but different radii. So this shape, so these are the points and f of z is analytic within the ring shape which is formed with the concentric circles C1 and C2. So here if you take any point, see f of z be analytic on C1 and C2 and throughout the region between the two circles. Let Z be any point in the ring-shaped region. So, Z be any point between the ring-shaped region between the two circles C1 and C2. Then we have to prove this. So, A1 is equal to this one and B1 is equal to this one. Now, we have to show this. So, in order to show this, I am going to use Cauchy's integral formula. So, according to the Cauchy's integral formula, we have, see, in the proof. So I am taking the Cauchy's integral formula. So in the Cauchy's integral formula, we have if f of z is analytic on C1 and C2, then f of z is equal to, see here, this is 1 by 2 pi I integral C1 f of z dz by this one is z minus a minus 1 by 2 pi I integral C2, this is f of z dz by this value is z minus a. So here the point z lies in the ring shaped region. So the ring shaped region we'll get by subtracting C1 minus C2. See here, this is a C1 and this is a C2. So generally this is Cauchy's integral formula, and in order to get the ring shaped region where z lies within the ring shaped region, therefore f of z is equal to integral C1 minus C2. And now let's get started to solve this. So in order to solve this, I am going to replace, see here, first thing is we have to replace z by t. And next, in place of a, I'm writing z. So this is the first thing you have to do. And the thing is, see here, f of z is equal to, so f of z is equal to, this is 1 by 2 pi I times of, in place of z I am writing t. So this will be f of t into dt by, in place of z I am writing t and in place of a I am writing z. Clear? Minus, this is 1 by 2 pi I times of, this is circle C1 and this is circle C2. In place of z I am writing t. So this will be f of t dt by, in place of z I am writing t and in place of a I wrote z. Clear? So the next thing is f of z is equal to, see, f of z is equal to 1 by 2 pi I integral C1. This is f of t dt by t, and now I am introducing, so in next step I'll do. So this is t minus z. So this is t minus z minus this is, so this minus I am making plus. So this will be 2 pi I times of C2. This is f of t dt by So I am taking minus common from this. So this will be z minus t. Clear? And the next thing here is what I am going to do is, so f of z is equal to, this is 1 by 2 pi I times of, this is a circle C1, and this is f of t dt by t, and now I am introducing 1a. This is minus a. In order to balance, and I am keeping plus a minus z, plus this is 1 by 2 pi I times of, this is f of t dt by z, and again I am introducing a. So this is minus a plus a, and next thing is minus t. Clear? Till here it's okay. And next one, first thing is, according to the Cauchy's integral formula, we have this one, and later I replaced z by t and a by z, and the next step I have taken is, I have taken minus common from the second integral, and I have introduced minus a and plus a in between t and z, and this time f of z is equal to, see here, f of z is equal to, this is 1 by 2 pi I integral c1 f of t dt, and see here, this is t minus a. I am taking minus common from this. This is z minus a. And from the second integral, this is 1 by 2 pi I integral c2. This is f of t dt by, here also, this is z minus a, and I have taken minus common, and this will be t minus a. Clear? See here. Next step is f of z is equal to, so f of z is equal to, this is 1 by 2 pi I integral f of t dt by, if I have taken t minus a common, this will be 1 minus, this is z minus a by, this is t minus a. Clear? And here also, this is 1 by 2 pi I c2, this is f of t dt by, if I have taken z minus a common from the second integral, this will be 1 minus, this is t minus a by z minus a. Got it? And the next step is f of z is equal to, see here, this will be 1 by 2 pi I integral, the first one is c1, this is f of t dt by, this is t minus a, and I am taking this to the numerator. This will be 1 minus z minus a by t minus a whole inverse. Clear? And the next one here is, this is 1 by 2 pi I integral c2, this is f of t dt by z minus a into 1 minus, this is t minus a by z minus a whole inverse. And see, we have an expansion from binomial theorem. So, according to the binomial expansion, we have 1 minus x whole inverse is equal to, this is 1 plus x square plus x cube plus and so on. So, I am treating this as 1 minus x whole inverse. Here also, this is 1 minus x whole inverse. So, now I am going to expand these two. See, f of z is equal to, see, f of z is equal to, this is 1 by 2 pi I integral c1, this is f of t dt by t minus a, and see, this will be 1 plus x square plus x cube and so on. So this whole thing is x for me. So this is 1 plus, this is z minus a by t minus a, plus this is x square z minus a square by, this is t minus a whole square, and next one is z minus a whole cube by, this is t minus a whole cube plus and so on. Clear? Next one, so this one is plus 1 by 2 pi I integral c2, so this is f of t dt by this value by z minus a. So if I expand, so this is of the form 1 minus x whole inverse. So if I keep in this will be 1 plus x square plus x cube and so on. So again I am writing, that is 1 plus x. So in place of x we have t minus a by z minus a, plus this is x square t minus a whole square by z minus a whole square, and next one is t minus a whole cube by this is z minus a whole cube, plus and so on. Clear? Now I am going to multiply with t minus a. I am sending this t minus a inside and z minus a inside. See, the next step will be f of z is equal to, see here, f of z is equal to, this is 1 by 2 pi I integral f of t dt by, if I send this inside, this will be 1 by t minus a, plus this is z minus a by, this is t minus a whole square. So this is z minus a whole square by, so if I send it inside, this will be t minus a whole cube, plus and so on. And the next step here is plus, this is 1 by 2 pi I times of integral c2, this is integral c1, so f of t dt into, if I send inside, so this will be 1 by z minus a, plus if I send this inside, this will be t minus a by z minus a whole square, and if I send inside, so this will be t minus a whole square by, this is z minus a whole cube, plus and so on. Clear? And see, now I am going to write these two terms as f of z. See here. This can be written as, see, I am going to write in this way. If you agree, I'll just want. So I am writing this as sigma 0 to infinity. See, sigma 0 to infinity. This value will be z minus a whole power n. Clear? So here z minus a power 1. So I am showing here, this is z minus a power 1. So this is z minus a power 1. So this is z minus a whole square, and this is z minus a power 0. So if I keep 0 here, so I'll get this one, z minus a power 0, anything to the power 0 is 1, z minus a power 1, z minus a power square, plus and so on. I am sending this outside, and I am writing the rest as 1 by 2 pi I integral f of t dt by, this value is, see here, this value I can write as t minus a power n plus 1. See, why n plus 1? If I keep 0 in this, so this will be power 1. So if I keep 1 in this, I'll be getting 2. If I keep 2, this is cube. Clear? Next thing here is, so this term I am writing as, see, this can be written as sigma n is equal to 1 to infinity. So I'm starting with 1. Why 1 here? So this can be written as 1 by z minus a power n. See, I'll show you how. If I keep 1 here, so I'll be getting z minus a power 1. If I keep 2 here, I'll be getting z minus a square. If I keep 2 here, this is z minus a square, and if I keep 3 here, z minus a whole cube, and the rest I'm writing as 1 by 2 pi I integral, this is f of t dt, so this is f of t dt, clear, by, this is t minus a, so this is 1, so I am writing this 1 as n minus 1, power n minus 1. If you check this one, if I keep 1, 1 minus 1, 0. So this is 0. If I keep 2 here, so this will be 2 minus 1. 2 minus 1, it is power 1, t minus a power 1. So if I keep 3 here, 3 minus 1, 2. So got it? So I wrote like this, and here I am writing this statement as f of z is equal to, see, I am writing this as sigma n is equal to 0 to infinity z minus a power n into, so this whole term I am writing as an. So this is an. Which an? Sigma n is equal to 0 to infinity an, and the next one here I'm writing as sigma n is equal to 1 to infinity. So this is 1 by z minus a power n into this one I am writing as bn. See here, an and bn, where an can be written as, so what is an here? So an is equal to the whole thing, this one, that is the whole thing is 1 by 2 pi I times of integral f of t dt by this is t minus a power n plus 1. Whereas bn is equal to, so in place of bn we have 1 by 2 pi I times of this is f of t dt by, so if I get it down, so this will be t minus a power, this is minus n plus 1. Clear? So what is Lorentz theorem statement? See, if you check this Lorentz theorem statement, so it is nothing but f of z is equal to sigma n is equal to 0 to infinity an into z minus a power n plus sigma n is equal to 1 to infinity bn by z minus a power n. So we got the same thing here. Therefore, we got f of z. So f of z is equal to, according to the statement, sigma n is equal to 0 to infinity. See, I am writing. So this is sigma n is equal to 0 to infinity a n into z minus a power n plus sigma n is equal to 1 to infinity. This is b n by 1 by z minus a power n, where a n is this one and b n is this one. Hence, this is the Lorentz theorem proof. See, let me explain you. This is very easiest the proof, and as you check this Taylor's theorem proof, so both are very similar. So please go through that video also. Lorentz theorem. So let f of z be analytic on two circles C1 and C2, which are concentric circles throughout the region between the two circles. Let z be any point in the ring-shaped region between the two circles. Then f of z is given as sigma n is equal to 0 to infinity a n z minus a power n plus sigma n is equal to 1 to infinity b n by z minus a power n, where a n is this one and b n is this one. So this is the shape. So this is circle C1 and this is circle C2. So A is the same center for both C1 and C2 as they are concentric circles, and R2 is the radius for C2 and R1 is the radius for C1. So clearly C1 circle is greater than C2. So in order to get the ring shape, C2 should be subtracted from C1. So according to the Cauchy's integral theorem, see here, this is C1 and this is C2, and there is a subtraction as it is given that z is any point in the ring-shaped region, and f of z is defined as 1 by 2 pi times of integral C1 f of z dz by z minus a minus 1 by 2 pi times of f of z dz by z minus a. First thing is we have to replace z by t and a by z. So I've replaced z by t and a by z. In the second step, I have taken minus common from the second step, and this become plus, and later have added and subtracted a from these two integrals. And the thing here is, the next thing is t minus a, minus I have taken common from these two and minus I have taken common from these two. So t minus a is taken common, here z minus a is taken common. Here it is the denominator is sent to the numerator, and here also denominator is sent to the numerator. According to the binomial expansion, this is the expansion. I have expanded both terms and have sent this t minus a inside and z minus a inside in the next step. And later, so this is very clear. So this step can be written as, so it is t. So integration with respect to t, and there is no t term here. So it should be treated as a constant. So if I send it outside, so this will be sigma n is equal to 0 to infinity t minus a z minus a power n. See here, if you put n is equal to 0, anything to the power of 0 is 1. If you keep n is equal to 1, this term, n is equal to 2, this term. Clear? And the rest is 1 by 2 pi I times of integral f of t dt by down. This is t minus a power n plus 1. Keep 0, 1, 2, 3. You will be getting those terms. And next one here, the second term. So here also, it is the integration with respect to t. And you can treat z minus a as as constants. So if I bring it outside, so this can be written as sigma n is equal to 1 to infinity 1 by z minus a power n, and the remaining thing is 1 by 2 pi I f of t dt, and here t minus a power n minus 1. If you keep n is equal to 1, anything to the power of 0 is 1. If you keep n is equal to 2, so this will be power 1, next one 3, it is square, and so on. So here this term I'm writing as an, and this term I'm writing as bn. So this is nothing but the Lorentz theorem statement. So f of z is equal to sigma n is equal to 0 to infinity an. This is z minus a power n, and sigma n is equal to 1 to infinity bn, 1 by z minus a power n, where an is this one and bn is this one. Hope you all guys understand clearly. If you understand, please pass it on to your friends. Please practice. Definitely you can score more, and go through the playlist, and so many useful videos are available there. Thank you so much.